So today I want to talk about model selection, which is maybe the conceptual main idea or the main concept of the whole course. So far you have learned many different models and I will recap them in a second. But the key thing of machine learning is how to choose the best one, how to choose between many different models. And we will start to talk about certain techniques that can be used for selecting the best model today. This lecture is based on chapter 6, mainly of chapter 6 of my book, chapter 6.1 till chapter 6.3. Okay, so when I say model, I don't mean Johnny Depp or Claudia Schiffer. I mean a hypothesis space. So I use the term model for a hypothesis space, and I will recap in a second. A hypothesis space is just a set, typically large, typically infinite set of different hypothesis maps. So what I want to teach you today is that modern machine learning methods use extremely large hypothesis spaces. And that's a problem. On one hand, this is good because in a large hypothesis space, you most likely will find the right one for your application. You most likely will find one hypothesis that is able to predict if an image shows a cat or not. So this might be a very nonlinear hypothesis, and a large hypothesis space might contain it. However, there's also some problems and challenges coming with large hypothesis spaces. In particular, you might run into overfitting. So we'll tell about overfitting, and then we will see how to first diagnose overfitting and then how to avoid overfitting using validation. Validation is a very simple idea, which I will explain in detail. And then once we have validated a machine learning method, we can choose between different models. So we can do model selection. And I will tell you in detail how you should choose the model based on validation errors. But let's start with a course recap. So far you have heard many different methods for machine learning, but they all follow a same principle. And this principle is based on 3 components. So now I would like to ask you, what are the 3 main components of machine learning? Now you can write it on the chat. Very good. So many of you have already internalized this 3-component picture, which I like very much. So we have data, first component, second component is a model, and we will talk about how to choose a good model today. And third component is the loss function. First, data. Data, I define as a set of data points. Data points can be anything, just an atomic unit of information. A data point is characterized by various properties. Some properties are easy to measure in an automated fashion. We call them features. And other properties of a data point are not so easy to measure by hard or software, but they are higher level facts, like if a patient has a COVID-19 infection. And for determining these labels, we need typically human experts. We need a doctor. We need somebody who studied medicine for 10 years. But machine learning then provides us a way to imitate this labeling of data points. So we start with some data points for which we know the label. For example, here, if the data point is a ski day and the quantity of interest is the maximum daytime temperature. So I can get examples of data points for which I know the label if I look into the past. So I look into these nice webcam snapshots that are available for all ski places all over Europe, and then check, okay, what was the maximum daytime temperature for that day? And then I get a bunch of data points. And once you have this bunch of data points for which you know the labels, this is kind of the starting point of applying machine learning methods. Yeah, in this course, we mainly consider data that can be represented as a matrix, so or a NumPy array for those of you who use Python. So we always try to gather the data or the feature vectors of the data points into a matrix. The number of rows here is M, is the number of data points. This is an important characteristics of a data set. Typically, the more data points we have, the better. So the larger M, the better. And then we have another key characteristic of a data set, which is the number of features. And then you would also think the more features, the better. However, it turns out that using too many features might be detrimental because it might confuse or mislead machine learning algorithms, so to say. So this is a bit more subtle here. The question if we should more features or less features. Then just as a reminder, it's always a good idea first to look at data, try to get a look at data using a scatter plot. This you can do easily if you have data points here which are characterized by a single numeric feature and a single numeric label. Then you can plot it in a two-dimensional plane, and then you see maybe some cluster structures. So some data points, some groups of data points are more similar than others. So it's always a good idea to do a scatter plot and try to get a feeling for the data. Okay, that was the first and maybe the main component of machine learning, data. Then what we would like to do in machine learning is we would like to find a good hypothesis. So what do I mean by a hypothesis? It's a very simple concept in principle, because I think everybody of you has learned the concept of functions or a map. And a hypothesis is nothing but a map. A hypothesis is a map that reads in all the features of a data point. Here in this case, it's only a single feature whose number is -10. It might be also a vector of features, a very long vector of features. So in modern machine learning applications, we use data points which are characterized by feature vectors of length billions. So evaluating such a map might be highly non-trivial already. But conceptually, a hypothesis is just a map. So we read in a feature, the features of a data point, and we get some output. And the output of a hypothesis we use as a prediction or approximation or a guess for the true label of a data point. So that's why we have here y hat. This is only an approximation of the true label y. In general, y hat will be different from y. And the goal of machine learning, roughly speaking, is to find a hypothesis or to learn a hypothesis such that y hat is always as close as possible to the true label y of a data point. Yeah, here's one example of a model or hypothesis space. This is the model given by all polynomials with maximum degree 1. And this is exactly the set of linear functions. So each line that you see here is one example of a hypothesis. This orange straight line is a hypothesis map. These dashed lines are hypothesis maps. And all these hypothesis maps together, they make up model 1, the model given by the degree 1 polynomials. How large is this model? How many elements does this model have, by the way? Does anybody know? Infinite, yes. I have shown here only 1, 2, 3, 4, 5, 6 representatives, but if we consider all degree 1 polynomials with a real valued variable x, then this is contains infinitely many. So we always use rather large models or hypothesis spaces. Here's an even larger hypothesis space, which is the hypothesis space or model given by all degree 3 polynomials. So this is the set of all functions that are given by a degree 3 or by a polynomial with maximum degree 3. And this, of course, is larger than degree 1 polynomial because any degree 3 polynomial, the set of polynomials with degree at most 3 includes as a subset all the polynomials with degree at most 1. So model 2 is larger in a very strict sense than model 1. Another example for a model, which you have heard in more recent lectures by Professor Sick, is about decision trees. So decision trees, again, is just a set of different maps. Here I have shown two such maps. So this blue map is represented by this flowchart or decision tree here. So it tests if the feature is larger than 2. Yes, then it outputs 0. If the feature value is not larger than 2, so small or equal than 2, then it outputs 2. So this graphical structure here, or decision tree, is just a representation of a map, of a hypothesis map. And we can have different such graphical structures or decision trees. For example, here we use a different threshold. So here we test if the feature is larger than 4, and we use then different values, output values on the leaves. So we call these elements here leaves because there is no further branch continuing from here. So this is another map. So this decision tree represents the red, the map with the red curve, and this represents the blue map. And learning a decision tree means out of all these functions, out of all these possible decision tree structures, which one is the best? Okay. So this is another model. Yet another model you have heard in the lecture about instance-based methods, which is called nearest neighbor. And this uses hypothesis maps that are defined by the data set. And this is a bit different to the previous ones. So here, for the previous examples, I didn't show you any data points. So the decision tree is a set of functions or maps that is defined without reference to a specific data set. Also, the set of degree 3 polynomials is a set of functions without an explicit reference to a data set. But we can also construct models by using functions that are based or that are defined using data points. And that's what called instance-based methods, because they use the instances, and instance means here training data points, to define a map. And in this case, we define a map that is given by the function value, by the label value of the nearest data point. So here in this range, the nearest data point is this here. So the function value here is 2. In this range here, the nearest data point for all these feature values here is this data point, and the function value is 1. And here, I think it's 1.5. So this is an example of an instance-based method because it defines the hypothesis space or model by referring to the data points. But in the end, it's just another way to construct a set of possible hypothesis maps. So this is just another model. So we have now 1, 2, 3, 4 models. And today I will talk about methods that allow to tell you how to choose between these different models. That's what model selection is about. Okay, last component. We had now main component data, second component model or hypothesis space. The third component is a loss function. So we need some measure that allows to tell, for example, when I look at this, this model here, consisting of many degree 1 polynomials, which one should I choose? So per se, if I don't have any error measure, I don't know which one would be the best. And machine learning tries to learn the best possible hypothesis. And in order to define the meaning of best, we need a loss function. We need to measure how good is a hypothesis map. And in the end, such a loss function is just a function that takes the differences between the predicted label. So this is y hat. Y hat is the predicted label that we get when applying a hypothesis map to the data point xi, minus the true label. So this yi is the true label of a data point. And then the difference is the prediction error. And one example of a loss function is the squared error loss. So I just take the square of the prediction error, and this here I use as a measure for the loss. Sorry, I need the pen. So this here is the squared error loss for the ith data point. And then it makes sense to average these individual losses for all data points and compute the average. So dividing by the number of data points. So this is the average loss. And in this case, it's the mean squared error because we'll use the squared error loss. However, there are many other choices for loss functions. And by no means the squared error loss must be the most suitable in your case. Okay, now that we have the 3 components, how do we plug them together? As it turns out, all machine learning methods that you might know, they are just combinations of these 3 of specific choices for these 3 components. So linear regression is one example. Deep learning is another example. They are all based on combining these 3 components, but they differ in how which model they use. For example, linear regression uses as a model the set of linear maps, whereas deep learning uses as a model the set of nonlinear functions that are represented by a graphical structure, which we call artificial neural networks. So different design choices for these 3 components give different methods. And you can see an overview of these different methods and how they are obtained from these 3 components in chapter 3 of my book. Okay, so, but how do we combine those three components? Well, it's quite natural to choose the hypothesis H out of the model that has the smallest training error. I mean, this makes perfectly sense. Find the linear, the straight curve here, for example, that gives the smallest average squared error. That's the key principle of most machine learning methods. Out of all possible hypothesis maps that you have in your model, pick the one that has the smallest average loss on your training set. So you could say that this optimization problem defines machine learning. So machine learning is a specific optimization problem, and machine learning algorithms in turn are optimization algorithms. Okay. So far, so good. So I will now make a short break here. Do you have any questions up to this point? There's one question. Could you quickly recap what is the loss function used for decision trees? Well, when you say decision trees, or when one says decision trees, one typically refers to a specific model, which means a specific type of maps. And you can use different loss functions. So you can use the squared error loss to measure the quality of a decision tree, or you can use the absolute error loss. So you can use different loss functions for decision trees. The choice of loss function also depends on the type of label values. So if the label is discrete, so you only have two possible label values, then you might not choose the squared error loss, but you might use a logistic loss. You can also use decision trees with logistic loss. So decision trees you can combine with several different loss functions. Another question, are there any machine learning methods that do not take the models with the smallest loss? Yes, we will talk about this in the next week's lecture about regularization. In regularization, we are not only interested in getting a small loss on the training error, but we're also interested in getting a simple predictor map in a certain sense. So there are methods that not only go after this. So this is kind of the naive approach to machine learning. This is the most basic approach. If you have enough data points, and you have you have chosen a good model in a specific sense, then this basic optimization problem is all you need, and solving it solves your machine learning problem. However, as soon as you have too little data, this is not a good choice. And we will talk about regularization techniques, which use a different objective function than this one. Okay, another question. Are there some other models than linear or polynomial models to solve regression problems, and which? Yes, so a regression problems refers to the fact that the label values are numbers. So regression problems point towards using a specific loss function, in particular the squared error loss. A regression problem can be solved with any model. So you can use nearest neighbor for regression problems. You can use decision trees to solve regression problems. You can use polynomials to solve regression problems. You can use artificial neural networks. This is, so to say, a different dimension. Regression or classification refers to the loss function, which loss function you should use. There are certain loss functions which are good for regression problems, but not for classification problems, and vice versa. There are some loss functions that are not good for classification problems, like the squared error loss. But which model you use is a different aspect. So you can use any model that you find in my book for regression problems or for classification problems. The fact if it's a regression or a classification problem mostly influences your choice of loss function. Yeah, that was a very good question. Thanks a lot. Another question, is the squared error loss always optimal for linear regression? What about regularized linear regression? Yes, so there are two different things here. regularized linear regression is not a different loss function, but it's a different way to learn, or a different principle to learn a good hypothesis that has a small average squared error loss. But the question then, if the squared error loss is a good choice, is not, there is no mathematical answer for that. It's to some extent, it's depending on your customer. So if you are a machine learning engineer and you have to solve a machine learning problem, then your customer might tell you, I want to know the prediction error as a mean squared error. So this is something that maybe the customer or the final user fixes the choice of the loss function. But it's not, there's by no means the squared error loss is always or should be the first and best choice for regression problems. It's just, it has nice computational properties, so we can minimize the squared error loss using a simple method called gradient descent, and it can also be interpreted as a statistical inference methods if you assume that your data is drawn from a Gaussian distribution. Then you can show that in some sense the optimal choice is a squared error loss, but this optimal choice depends on a probabilistic model, and you never know if a probabilistic model is true. So it's again just an assumption. Another question, you mentioned that there could be millions of features. How often is dimensionality reduction such as PCA used? Very good point. Yeah, so as I discuss in my book, in modern machine learning problems, we typically have too many features. Just look at if you use a data point to represent an image or a snapshot that you take with your smartphone, and you use as a natural choice for the features, you use the pixel intensities. So a smartphone has megapixel cameras. So already here you get feature vectors of millions length, or containing millions of entries. And in such applications, it's de facto standard to do some dimensionality reduction like PCA. So using PCA is not exotic. I would say it's rather the regular use pattern of machine learning methods. Okay, then another question, could you suggest some loss functions that are most suitable for the classification problem? Yes, you have heard in the recent lectures different loss functions for classification problems, and also in the book you can read in chapter 2 and chapter 3, for example, logistic loss is a good choice for classification problem. Then the hinge loss, which is used in SVM methods, is a good choice, or the 0-1 loss. So the 0-1 loss is 0 if the predicted label is exactly the true label, so correct prediction, or the loss is equal to 1 if the predicted label is different from the true label. So this means an error. Yeah, the 0-1 loss is also goes under the name of accuracy. If you average the average 0-1 loss, when you average the 0-1 loss over a training set, then you get kind of the fraction of misclassified data points. So this is also called, so it's not accuracy, it's 1 minus accuracy, to be precise. Another question, does K nearest neighbor use some kind of loss? As I understand, it doesn't minimize any loss or function to optimize the weights. Very good point, yes. This is a bit a special case, because in these instant-based methods, the model is quite simple, because if you define the model as the nearest neighbor map, then this hypothesis map is fully specified by the training set. So this model consists of exactly one single map. So there's not much to optimize. So there is no point to use, to use a loss function here, because by the characteristic of the model, there is only one single predictor map, and there is no need to choose between different predictor maps using some loss. However, we will hear today how to handle a list of different models. So you could have one model which is k nearest neighbors with k equal 2. Then another model, which is k nearest neighbors with k equal 3. And then you can compute for these different models the validation error. And for this validation error, then you can choose a loss function. And here again, you can choose different loss functions. So there's no single optimal loss function for nearest neighbor methods. Again, you can use the squared error loss or logistic loss if it's a classification problem. Okay, any other questions at this point? Yeah, so do you hear me loud and clear, or is it very low, the sound? Okay, now I'm speaking a bit louder. Okay, thanks a lot. Yes, it's good now. So then there's another question. Now I'm scrolling up. The question is, if we can approximately determine the distribution function of our data points, how can this contribute to our machine learning model? So if you talk about the probability distribution of your data points, if you know the probability distributions from which your data points are drawn, and you never know this in practice. You never know if data points that you collect, that you have in your CSV file, are realizations of a random variable. That's just, again, a modeling assumption. But many people use such probabilistic models. And if you have such a probabilistic model, then all we talk here about pretty much becomes trivial, because the optimal hypothesis is given by a formula. So you can write down in closed form the optimal hypothesis, which is called the Bayes, sorry, the Bayes estimator. But this you can only do if you have the probability distribution, or if you assume a probability distribution underlying your data points, which we do not do in this course. But if you have such an assumption, then you can calculate the optimal hypothesis in closed form. It's just essentially an application of the Bayes rule to compute the conditional probabilities. But this is not the scope of this course. There's a nice course by a colleague of mine called Bayesian data analysis. So in this course, you mainly use probabilistic models for data. And once you have a probabilistic model, then you don't need to do this optimization problem here. You can write down the optimal hypothesis, which is called the Bayes estimator. Another question, are the loss functions you mentioned just now also usable for multi-class classification problems? So the loss functions I refer to mostly in my book, they are applicable for binary classification problems. So you have either y equal 1 or y equal -1. Such type of problems. And if you have several classes, like you not only have cats and dogs, but different types of dogs, different classes of dogs, then you can reduce it to binary classification problems. So there's a neat trick to reduce a multi-class problem to several binary classification problems. Sorry. So this is called one versus all, or one versus rest, this trick. And if you Google this trick, you will find, I will not discuss this in more detail. For your student project, machine learning project, it's totally fine if you, right from the start, only consider binary classification problems. There's no need to consider multi-class problems. But if you're interested, then I would look up this technique called one versus all, or one versus the rest, which is a very simple approach to reduce a multi-class problem to a small set of binary classification problems. Okay, there's another question. So optimization algorithms just find the best weights, and loss function is the final step of evaluating the model of those weights. Almost. So we use an optimization algorithm to solve this optimization problem. So we get this is called training. So solving this problem is called training. We train a model. And the hypothesis, H hat, that we get out of it is in some sense the optimal hypothesis, in the sense of having minimum training error. But in order to evaluate the quality of the hypothesis, we will now see that this is not a good idea. And I will show you why. So let's consider two different models. So model one, again, a polynomial with maximum degree 1. And we use an optimization algorithm to find the particular hypothesis out of this model. So we find that particular hypothesis, which is a polynomial with maximum degree 1, which has minimum squared error loss on the training error. Okay, so we fit we fit we call this also fitting a straight line to these data points. And then we do the same. We now train the other model, model 2. Model 2 is given by all polynomials with degree at most 3. So we again, we fit this model to these data points. And you see, somehow it looks better. So larger model gives us more flexibility to better train it on the training set, to get a smaller training error. So it's trivial that the larger model you use, the smaller training error you get. So if I fit a degree 1 polynomial, I get some training error. So I get the best possible average squared error by a linear curve, which is non-zero typically. If not by accident, all these data points line up on one curve, I will never get zero training error. However, if I use a polynomial with very large degree, in particular if the degree is as large as the number of data points, then you can use a basic result of analysis of mathematics that tells you you can perfectly fit almost any set of data points with such a polynomial. So you get the training error to 0 for large enough degree. And this is a general behavior. The larger model you use, the more choice you have to choose from different hypothesis maps, and the more likely it is that one hypothesis map will almost perfectly fit your training data. And so is this now good? Is this a good idea now to choose the model which has the smallest training error? No, it's not a good idea, because you're not actually interested in a small training error, but you're interested in how is this hypothesis doing when you apply to new data points. So imagine you train some hypothesis that you use to predict some quantity, like the delivery time for a food in some delivery service. So then you have a database of previous orders and delivery times. So this is your training set. You train a hypothesis on your training set, and then you apply it to a new data point. And having a small training error can mean nothing regarding the accuracy on a new data point. And this is called overfitting. So we perfectly fit the training data because we use such a large model which just contains so many nonlinear functions that mostly by pure luck we find one nonlinear function that perfectly fits the training data points. However, this nonlinear function does not good at all. It performs very poor on data points outside the training set. And the basic idea is now validation. And the validation is done by a simple trick. I would not even call it a trick, but a procedure, which is to split all data points that you have. So these blue dots are all the data points that you have, which you have in your database or in your CSV file, wherever you get your data from. And you split them into two subsets, which are non-overlapping. One is called the training. One is used as the training set to find the best hypothesis in the model. And the second one is used to probe the learned hypothesis, how it would behave outside the training set. And here I now started to try to put some code snippets from Python. So if you're not using Python, no worries at all. You don't need to understand this. But those of you who use Python, I just want to point out that splitting this data set into 2 subsets is easy. It's 1 line of code. It's the function called train test split. Okay, and then after we have split the data into a training set and a validation set, we do as follows. We do, for the first model, we find the optimal hypothesis. We find the optimal hypothesis in the model 1, which is the set of linear curves. And then after we have optimized this straight line using those blue data points, the training set, we validate it, we probe it by computing its error or loss on the validation set. And then we do the same, exactly the same for the other models. So we fit the degree 3 polynomials to these blue data points. So we try to find the specific hypothesis of degree at most 3, which has the smallest training error relative to these blue data points. And after we have trained it, after we have minimized this training error, we then apply it and try it out on this validation set. And here the validation error is much, much larger all of a sudden. So here's a simple code snippet that shows this workflow. We first train a model using the .fit function. So in Python, you have for almost all popular machine learning methods, you get some method called model.fit. And calling this function model.fit does the following. It solves this it solves this optimization problem. So no need for you to solve optimization problems with pen and paper. This argmin, solving this optimization problem is done in most cases by 1 line of Python code, this .fit function. So here we train the model, then we compute the resulting training error, which is typically very small because we optimize the model on the training data set, so the training error will be small, but we also compute the validation error. And this is kind of a key requirement for the student projects. I want every project to contain a training error and a validation error for every machine learning method that you consider in your report. Okay, so there are several variations of this basic idea. The basic idea is always the same. Partition your data set into subsets, use some subset for training and the other subset for validation. However, if you use only this single split here, you might be very unlucky. So in particular, if you have a small data set, so we here have 4 data points. So we have a data set with only 4 data points. And we randomly split it into a validation set and a training set. And here you see we have been very unlucky in this split because the data points in the training set, they behave very different than this data point in the validation set. If you look at the validation error here of this dashed curve, it's 0, essentially 0. So the validation error here is much smaller than the training error. And this makes not much sense. So the hypothesis that we learn here from this training set and the validation error of this hypothesis might be highly misleading because if we then look at the validation error, almost 0, we might say, ooh, that's good, a good model. However, this validation error was just an accident, so to say, because we made an unlucky split. And in order to avoid such an unlucky split, we often use k-fold cross-validation. And the idea of k-fold cross-validation is simple. Just repeat this split several times so that you average out possible unlucky splits. So we have k, the number k here means the number of repetition. So if we use k equal 3, we divide the data set into 3 equal blocks. And in each iteration or each repetition, we choose 1 block as the validation set and the remaining blocks as the training set. Then we use the next block and the next block and so on and so forth. I guess no, k here should be 5 because we have 5 data points and we divide the data set into 5 blocks. So here, these are the first 3 folds. Total, we should have 5 folds because each block, and the block here is a single data point, should be once used as a validation set. So yeah, if you send messages, please make sure that you send it on the public chat so that others can follow the questions. Just as a side comment. I will then answer the questions again in the next break, which will be soon. So now we have k-fold cross-validation is almost the standard method to do validation because, as I said, we average out over unlucky splits. In particular, if we have small data sets, like only 4 data points here, there's a non-zero probability that we have a very unlucky partition into validation and training set. And in k-fold cross-validation, such unlucky splits don't have such a big effect because they are averaged out in some sense. Okay, and now the basic idea of model selection is quite simple. So for each model, we train the model, get a training error and validation error, and then we pick the model which has the smallest validation error. So that's quite simple. So I will now make again a short break and answer all the questions that have accumulated on the chat. There is one question. What is the difference between training set, testing set, and validation set? So I now explained the difference between training set and validation set, and test set I will discuss in a few minutes later. Are there some cases or projects in which the training and validation cannot be done in Excel and should be performed using Python? No. I have uploaded an example Excel sheet where we have also implemented validation. So the splitting into subsets you can also do easily in Excel. However, if you are familiar with Python, then this is really convenient. And I also recommend here at this point as a follow-up course after this course, if you want to learn Python, our course Machine Learning with Python, which will be like a piece of cake for you after this course. So I have just write the course name here. So then there were several other questions about k-fold cross-validation. We actually fit many sets, split it from the training set. So what will be the coefficient for testing data? Yeah, so far I didn't talk about testing data. I will then talk about testing data in a second. So we need one more data set later on. Then another question. So in your example, model.fit is the optimization and squared error loss is the loss function. Testing, validation, and training error. Yeah, I don't know what the question here is exactly, but yes. So in my example, I used the squared error loss for the training and the validation error. Yes. I'm not sure if this answered the question, but feel free to ask again or in a different form. Then another question, which of the splits to choose from the k-fold cross-validation? Or train the model with all splits? Yes, so you don't choose any single split. So this is a whole procedure. You go over all possible. So each of these subsets is once used as a validation set and the rest as training set. And you iterate over all possible permutations, so to say. And then you average the validation error you get for the first iteration with the validation error you get for the second, and so on and so forth. So there's no need to pick any iteration here. You compute the average over all iterations. Then another question, is there some certain ratio for the size of training and validation set that should be used in general? I will talk about it in a second, but in general, no, I cannot offer that. So it's often based on trial and error. So you must choose a certain size of the validation set to start with and then see if the result is meaningful in the end. For example, looking at the test error, which I will explain in a second. How to compute the test error. Then another question, does the k-fold split always assume some kind of ordering of the data, or does it randomize itself, or should you do it? Yes, so this, what I show here, this implementation of k-fold cross-validation only works if the data points are unordered. So the order, for example, the order of the rows in your NumPy array has no statistical meaning. In particular, you should not use this approach when you have time series data where consecutive blocks in your data set are correlated. And in this case, you should randomly shuffle them before. But I'm not sure, I think, or it might be that this k-fold cross-validation in Python at least does the shuffling for you automatically. Okay, another question. Can the accuracy of test validation set be used in selection of model in classification problem instead of loss? Yes, I will talk about this in a second. We can use different loss functions for the validation set and for the training set. In particular, when you look at logistic regression, this uses the logistic loss for the training to find a good hypothesis. However, to compare different classifiers, we typically like to use the 0-1 loss or the accuracy on the validation set. So you can do that. You can use a different loss for training the model and then for validating the model. Then another question. This week's quiz, will it be multiple choice questions or shorter answers? So the current quiz is again a multiple choice question, but now you have only one attempt. So in this quiz, you have only one attempt and you have to submit it till end of this Sunday. If you need further attempts, you will have the opportunity to answer quiz questions that you didn't get correct in one of the exercise sessions next week and get the points then from these sessions. Or if you're not comfortable with answering them in an exercise session, you can contact the core staff and arrange a Zoom meeting with us. Yeah, and this quiz contains only 5 questions, so it's shorter than the previous ones, and it's mostly based on this lecture. So if you carefully follow this lecture and the slides, you should have no problem. It should almost be trivial, this quiz. So I would not delay it till the end of the deadline, so on Sunday. Maybe you could try it today or tomorrow. Another question, so if you have time series data, how should the training and validation sets be chosen? I will not talk about this. So this is beyond the scope. There are entire courses on how to validate machine learning methods for time series data. So I will not touch this here. I'm sorry. Another question, was it that in empirical risk minimization, we did not need to split the data into training and validation because of the random variable assumption? Well, in empirical risk minimization means this training problem here. This training problem here is called empirical risk minimization. And what I refer to as training set, so whenever I say training set, I mean whatever data set you use here in this empirical risk minimization. So the data that you use here to learn the best hypothesis out of the hypothesis space, this is the training set. So ERM, empirical risk minimization, is always performed on the training set. Another question, so finally, we will choose the fold having minimum validation error. No, you don't choose any fold. You average over all folds. You average over all folds. And when you average over all folds, you get one validation error for a certain machine learning method. So you do k-fold cross-validation for logistic regression. You get a validation error by averaging over all folds. And then you do k-fold cross-validation for SVM classifier. And you get, again, an average validation error as an average over all folds. So no need to pick individual folds here. Okay, so then we'll now continue with my lecture. So the basic idea, as I said, of model selection is quite simple. Pick the model with the smaller validation error. And as I already said when answering the questions, sometimes it might be useful to use different loss functions for the training and the validation of a model. For example, assume you want to learn a classifier of images which classify an image either as cat or dog image. And you're not sure, you want to try out different machine learning methods. One such method is logistic regression, and another method could be support vector machines. And the difference between those two is that they use different loss functions. What is common between those two methods is they use the same model, actually, but they use different loss functions. So you could compare the hypothesis you get from support vector machines with the hypothesis you get from logistic regression by using their 0-1 loss on the validation set. But the 0-1 loss is different from the loss function that is used in logistic regression to learn a hypothesis, because the logistic regression uses the logistic loss to learn a hypothesis, and SVM uses the hinge loss to learn a hypothesis. However, to compare those two, it's better to use the 0-1 loss on the validation set, because then I can compare. I can say, aha, this hypothesis H1 got 90% correct on the validation set, and this other hypothesis I got, H2, got 95% correct on the validation set. So it seems that H2 is better. Yeah, and here I've shown a little code snippet where I train logistic regression and SVM. So here I define the object logistic regression, and the function .fit trains or searches for the best hypothesis with the smallest logistic loss. And I do the same with the support vector machine. So this .fit function here searches for the hypothesis with the smallest average hinge loss. The SVM uses the hinge loss. But in order to compare those two, so here I get one hypothesis, here I get another hypothesis. How do I compare those? Well, I compare them by computing the 0-1 loss on the validation error. So this .score function, this computes the 0-1 loss. And this is different from the logistic loss function that is used in the fit function here. Yeah, in your projects, when you solve classification problems, you might make use of this principle to use different loss functions on the validation set and on the training set, because you can compare easily accuracies of classifiers, but you cannot compare easily, for example, a logistic loss with a hinge loss or with a squared error loss. This doesn't make sense. These are different units in which the error is measured. But if you use for all the different methods on the validation set 0-1 loss, then you can easily or safely compare them with each other. Okay, so we already touched the notion of test set when answering the questions. What is the test set? Well, if you choose a model based on the validation error, then the validation error is not a good indicator for the performance of the resulting hypothesis. Why is that? Because you use the validation error to cherry pick the model. You choose the model. In fact, you choose the model such that its validation error is minimal. So of course, the validation error will be a too optimistic estimate for the performance of the chosen model. So what we need to do, well, we do the same as we did with validating a learned hypothesis. We need another set which has not been used for selecting the model. So we need another set, and we call this test set, which has neither been used for training a model nor for validating a model, because we use the validation errors to choose between different models. And as soon as we choose based on the validation errors are not a fair estimate anymore for the performance or for the average error on new data points. That's why we need a test set. So now we have all sets that we need today, which is a training set to train a model using empirical risk minimization. Then we need a validation set on which we validate the hypothesis that we get from training on the train set. These validation errors we then use to choose between all the different methods we had in our mind, like SVMs, logistic regression, artificial neural networks, all kinds of models we try out. And for each model, we compute the validation error. And then we pick the model with the smallest validation error. And the resulting model then needs to be evaluated on the test set. So the test error is the average loss that we get from the chosen model on the test set. Okay, so now I take some questions here. So that logistic regression, in logistic regression, the score as average 0-1 loss is suitable enough to compare how well the logistic regression fits. There is no need for other error functions in the projects. No, I don't require you to choose a specific loss function. If you use the 0-1 loss on the validation set, that's perfectly fine. Yes, but there are other loss functions. Other loss function for classifiers, I think, is called F1 loss. Then there's also something called area under curve and all kinds of fancy names. However, the 0-1 loss is perfectly fine for this course. Another question, very good question. Which library are you using in your Python examples? I'll use scikit-learn. And actually, my course structure is to some extent based on scikit-learn, because in scikit-learn, you have also this structure into rounds. So maybe I quickly show this. So scikit-learn. Can you see my browser? Yes, thanks. So this scikit-learn is really I would say, the standard tool for machine learning in Python, or for machine learning in general on a computer. And you have here also these modules: classification, which corresponds to our round on classification, largely a regression, which is the round on regression problems. And what is nice, so if you say in your project you want to do an image classifier, what you could do is you could go to image classification, scikit-learn, pick up an example there, recognizing handwritten digits. And they also provide demo code snippets. So you could copy paste these demo code snippets and then adapt it according to your needs. So this code snippet here implements a support vector classifier. It implements already also the splitting into training and validation or test sets, all here already. So you copy it and then you apply it to your own data. You just replace the part where the data is loaded. So here the data is loaded, and then here you load the data you would like to have if you want to use Python. You don't have to use Python. Another question, what do we have to do if the model doesn't work on test set? I don't know what you mean by doesn't work. So in this project, you are not required to achieve a certain accuracy level. We are not interested that you get a certain performance like classification accuracy above 90%, not at all. So it's about documenting your work. So which model did you use? How did you split your data into train and validation set? Did you use k-fold cross-validation? Which data did you use? This report is the main output and not a good classifier, not at all. So another question, is it necessary to have time limit in the quiz when there is only one attempt allowed? In terms of learning, it would be better to have time to search for the answers and understand the topic without having to stress about the time. Yes, I know that it's stressful, but also when you have a written exam, you have a time limit, and it's 2 hours. And I can tell you, the quiz is really mostly based on this lecture and the slides. So if you understand the slides, if you have carefully read through the slides, you should have no problem with finalizing this quiz in 2 hours. Okay. And yes, please note you have the options for bonus points. So I'm happy to get feedback on course material, particular pointing out typos, providing suggestions for improvement, working out some of the examples or exercises in the book. I will grant bonus points. And also, as I said, if you do not manage this quiz, to submit this quiz, you have the opportunity to answer the quiz questions during the whole next week in any exercise session or by a direct private chat with the course staff. So I really want to I don't want to stress you, but I also want to make the grading fair and also useful for the learning experience. Okay, another question. I'm a bit confused. Is it so that in the beginning we have many different methods, then we optimize a model for each training set, then we validate the model using the validation set? What are the models that we then compare to each other based on the test set results? At what point do we choose which method is best? Very good question, and this pretty much covers what I'm talking about. So you come up with a first guess for the methods. So I highly recommend that you use for your first guess some of the methods you have heard about in this course, in the lectures, or read about in the book, like linear regression for a regression problem or logistic regression for a classification problem. And then it's typically good to not only stick to one model or method, but two. So for classification, a good choice might be logistic regression and decision trees. Then for those two models, as you said, for each model, you train the model on the training set, compute the validation error on the validation set. Then you choose the model between those two. If you use two different candidate models, you choose between those two based on the smaller validation error. Then you did already model selection. And the final step is then on the selected model, with kind of the trained selected model, you compute the test error on the test set, and you report the test error. And then in the student report, I ask you in the final section, conclusion, you should speculate. Do you think that this test error is good or not? And I don't require you to give a definite answer. I just want you to think about it and write maybe 1 or 2 sentences. Because it's hard to tell if a test error is already optimal or not. In my book, and actually we will talk about this in the next lecture on diagnosing machine learning methods. In some applications, you might know a benchmark. For example, when you want to develop a classifier for X-ray images to detect a certain type of cancer, you might have an experience for the accuracy of experienced doctors, radiologists. What is their error rate? How often do they not find a tumor? And then you can use this error rate, let's say it's very small, 1%, as a benchmark. And if your final test accuracy is 10%, then you know you cannot beat the human at the moment. So this would be one way to compare against the benchmark from humans. Yeah, I hope this answered the question. Please ask more if you have more questions. Then another. Metrics accuracy score for multi-class classification, which loss function on it uses? I don't know. So please check out the Python documentation. It's pretty detailed and complete, I think. So if you Google this, a Python function, you should be able to dig out, well, but if I have it open here, let's give it a try. No, I cannot find it. But I recommend to read through this scikit-learn documentation. Another question. How to choose the confidence boundary. Yeah, this is beyond the scope of this course. So please ask this by email if you really need this. In the example, the scikit-learn splits the data into training and validation. Should you split into training, validation, and test instead? Yeah, so this depends. So I now go back to my to my PowerPoint. This depends. If you choose a model based on smallest validation error, then you need the third data set. Then you need the test set to evaluate the chosen model. But if you just want to make a study of how well are the models doing, so you just report a validation error for model 1, validation error for model 2, and write this in your report, then there's no need for a test set. But as soon as you then move on and choose a model based on the validation error, then you should use a test set to evaluate the quality of the chosen model outside the validation set. Yeah, this also addresses the next question. Then another question, could it be possible to add name of the symbols used in the machine learning book? Yes, so there is a section in the end, I guess it's chapter 12, symbols in the machine learning book. I'm not sure if it's chapter 11 or 12, but please, in the end, you find a list of symbols and their name. And I'm happy to receive any hints, and I'm giving bonus points for hints what to add to this list, what you would find useful. Then another question, when evaluating the final performance of the chosen model using the test set, which loss function should be used? Should it be the common one used for validation or a specific one that used for training the winning model? So the test error, this is something then you for example, forward to your customer or to your boss who ask you to solve a machine learning problem. And so this is what the customer wants. If the customer is only interested in a classification accuracy, then you use the 0-1 loss also on the test set. So this is often given by outside. So there's no natural or mathematical preference for a loss function on the test set. Yes, so does the accuracy in Python refer to 0-1 loss? Yes, so by accuracy, accuracy means the fraction of correct predicted data points. And this is the percentage of 1 minus the average 0-1 loss, because the 0-1 loss is 1 for every data point that is corrected, that is wrong, classified wrong. So if you average the 0-1 loss, average 0-1 loss is 1 minus accuracy. If accuracy is on the scale 0 to 1. So there's a direct relation, but it's not exactly the same. But I hope you get the point. Then another question, please a small description about the differences between image classification, segmentation, and clustering. Yeah, so I will talk about clustering in round 5. So we will talk about clustering in round 5. The difference between image classification and clustering is that for clustering, we do not need any labeled data points. So we just look at a bunch of images, but we do not need for any of the image if it shows a cat or a dog. Clustering methods do not need label information. That's why they're called unsupervised. But you can read about clustering in chapter 8 of the ML book, and we will have lectures on I will give lectures on them in round 5. Another question in the project, is it required to actually choose a model? Does have a test set, or can you just try out different models and report findings? No, so the test error is mandatory. Also the reviewer questions, and I also welcome you, highly recommend that you have a look at the reviewer questions that we have now put on the My Courses page. They ask each one of you to check if the report that you review or grade mentions the test set error. So this is mandatory. Another question, what kind of loss function would be preferred for validation in regression problems? So in regression problems, the standard choice for all tasks for training validation is squared error loss. I would not know any other good choice that is widely applicable. So the squared error loss is mainly the standard for any task for regression problems. Another question, I cannot find the first assignment of the course. Your problem on my courses. Yeah, I reorganized the, the section on the assignments, and you will find it on the bottom of the section. It's on the very end of the section because I want to have the current assignment on the top of the section. Okay. Yes, so I will now continue with the last few slides and then take any final questions. So now we have discussed the test set and now the final model selection recipe or model selection algorithm that you should implement also in your projects. You start out by a list of candidate models, and this is something you can freely choose. So one possibility could be when you have a classification problem, use as candidate models, logistic regression and decision trees, but you don't need to stick to these two models. Then for each model, learn or train the optimal hypothesis by minimizing the training error, and then compute the validation error of the resulting hypothesis that you got out of the training. Then, after you have done this, for each model, pick the model which resulted in the smallest validation error and the minimum validation error. And then for this optimal model, you compute the test error on the test set and you report the test error. And this recipe is pretty much the whole workflow of the student project. Okay, then we had before the question, how large should the validation set be? And it's different to come up with a general guidelines because this required size of the validation set depends very much on the statistical properties or on the distribution of the data sets. And we never know, we in practice never know the distribution of the data set because we can never say that a set of data or an Excel spreadsheet, the numbers in an Excel spreadsheet are realizations of a random variable. How could we ever test it? It's just would be a modeling assumption. But if we assume such a modeling assumption, it might be a good idea to assume such a model. This is in some sense also a hypothesis that we assume. So if you assume such a probabilistic model, like that the data are realizations of IID random variables, then also these losses for the individual data points. So I have showed here the special case of a squared error loss. This could be also a logistic loss. But in general, we compute the average loss over many data points or several data points in the validation set. And if these data points are IID realizations, then also these loss terms here are realizations of IID random variables. And what we then have here is an average of many IID random variables. And then some of you might have heard already, and some of you this might already ring a bell, those who had a course on probability theory, when you compute the average over many IID random variables, then you can use strong, powerful results of probability theory, which tell you that this average will become more and more concentrated around the mean, the expectation of these random variables. And the expectation of this individual loss components here, the expectation of Li, is the same for all data points because they are independent and identically distributed. That's why this expectation here is the same for all I, for all data points. And the mean of the validation error is exactly the mean of these losses, and the mean of these losses is exactly the average risk. So this here is the quantity that we are really interested. This is the average over an infinite number of data points, the average over the losses for an infinite number of data points. So this is what we're really interested in, the global average loss or risk. This is also sometimes called the risk. And it turns out that the expectation of this validation error that we compute is exactly this risk. However, what we compute is not this expectation, but we compute just a realization of this random variable, and it fluctuates around the mean. And the variance, that is kind of the strength or the magnitude of these fluctuations, is related to the variance of the individual loss functions by 1 over number of data points in the validation set. So the larger we make the validation set, the larger we make this MV, the smaller the variance becomes, and the more reliable this validation error will estimate the average risk of the hypothesis. So if you happen to know the variance of the individual loss functions, but this might be non-trivial already, you can use this formula here to bound or to lower bound, to come up with a lower bound for the size of the validation set. So how large must the validation set be at least to guarantee that the variance of this validation error, the variance of the random fluctuations, is less than 10 to the power of minus 3. Yeah, and then the question here is, of course, how do you get this variance for the loss components? And for this you must assume a probabilistic model. And I have worked this out in section 6.4 of the course book, where I assume a simple probabilistic model. So I assume that the feature vectors are multivariate normal distributed, and then I can write down formulas for the variance of the validation error. But how do you know the actual distribution? Well, there are certain statistical techniques to estimate, for example, the variance of a given series of numbers, for example, using this sample average. But this is well beyond the scope of this course. I just want to sketch how you could work out or how you could characterize the required size of the validation set. Another question, is it still possible for the model to be wrong if its validation error is the smallest? Yes, absolutely. Absolutely. In particular, when you are unlucky, when you have an unlucky split and you have a very small number of data points. So here you have a small data set, and you, by accident, you pick as validation set a data point that lies perfectly on one of the linear curves. So the validation error is 0, but this predictor map or hypothesis is not good at all when you look at the other data points. So it might happen, but hopefully with a small probability. Okay. Another question, we need large data to use this property. Well, it depends how large it doesn't depend on the, so this formula is exact. So if these are realizations of IID random variables, then the variance scales like 1 over number of components in the sum. So this is exact. However, if this number here is small, if the sample size is small, like 10 or so, then this variance might be too large. So in order to make the variance to be like 10 to the power of minus 6, you need here maybe 1 million. So a sample size of 1 million to really push down this variance of the fluctuation in the validation error. Okay. Another question, if the only difference between validation and test set is the error method, why do they need to be based on different data sets? No, so the difference between the validation and the test set is that the validation set has been used to choose the model. That's the difference. So therefore, we need a test set that has not been used for choosing any model or any weights in a model. Another question, for the project, shall we include training, validation, and testing error, or would it be enough with training and test, or validation and test? Yeah, so if you use several different models, you need a training set to train each model, you need a validation set to compare the validation errors, and you need a test set to compute the test error. So yes, you need 3 sets. Another question, can the project report be longer than 5 pages if it, for example, has very illustrative and helpful pictures that take a lot of space? No, we are very strict with the page limit. And also, you should not overdo with your project report. It can be related to a master thesis or even a PhD thesis or a work project, but keep in mind that you should not spend more than 130 hours on this course. So keep it simple. And I have put on the My Courses section an example for a report, which should give you an idea how much work you should spend on the report. Another comment in book page 113, it says, pick a hypothesis. Does this mean? Yes, so I have to check it again. Maybe it's not clear, but when you do no, now here in k-fold cross-validation, we only validate a method. So there's no model selection here. And by this H superscript B, I mean for each repetition in this k-fold, you have a different training set. And since you have a different training set, you will get a different hypothesis map because you minimize the training error on this set. Here in the second fold, you get another. You will get a slightly different hypothesis map because you minimize the training error on that different training set. So you get for each fold or each repetition, you get a different hypothesis. Yes, and then yeah, in the end, now I get the comment. Yes, and in the end, you pick because you need to pick some hypothesis. It's not so clear how to average the different hypotheses. It's rather straightforward to average the validation errors for each fold, but it's not so clear how would you average the hypothesis. And therefore, I decided as a variant, so you can also use different variants, to pick the hypothesis from that fold that resulted in the smallest validation error. Yes, very good point. Another question, do we create test sets simultaneously with validation and training sets, or do we create it after validation and training? So I would recommend you just use in the beginning, right after you're reading the data, you use one split into a train and validation set block. And the second component that you get out of it is the test set. And this test set you keep away. And with this training and validation set block, you do k-fold cross-validation, for example. I have written this down, I think, in algorithm 6 in the course book. Yes, another question. Shall we include the 3 errors in a table for the final report? It doesn't need to be a table. So if you just include it in the text, it's also fine. It just has to be there. Yeah, it seems maybe I have hidden the first assignment by accident. I will make it visible, so don't worry. It's all there. Okay, I don't know. Do I still have some slides? 2 slides. What's the time? Let's look at the time. Yeah, maybe I talk about effective dimension then next week. Let's see. Yeah, we don't need it for the. Now, I think, yeah, it would also be good in view of the quiz. Okay. So when we look again at this example of the 2 models, model 1 and model 2, model 1 was the degree 1 polynomial, model 2 was the degree 3 polynomial. And then it turned out that while the training error of this larger model 2 goes down, was smaller, the validation error went up. So remember what happened with this large model. It contained very nonlinear functions that do no good at all in the validation set. So we overfit. And the question now is is this a general behavior? So when the when the model is too large, and when exactly, what do we mean by large? When does it overfit? And for this, we need a measure for the size of a model. And remember, these models are hypothesis spaces containing infinite elements. So how do we measure the size of a set with an with an infinite amount of different elements? And there are different concepts. And I would like to use a very simplified version of a dimension. So maybe some of you have heard about the concept of dimension in linear algebra. And it's a bit similar to the notion of dimension in linear algebra. And I call it effective dimension. So the effective dimension D of a hypothesis space is the maximum number of arbitrary data points that can always be perfectly fit by some hypothesis in that space. So this effective dimension D is a measure for the size of a hypothesis space. And we will see that this size must be compared, or what is the crucial parameter is of a machine learning method is the ratio of the effective dimension of a hypothesis space relative to the number of data points M. So whenever this dimension or this effective dimension is much larger than the number of data points in the training set, there's a risk of overfitting. So let's look at some examples. Let's look at the effective dimension of linear maps. So let's say we look at the model given by all linear maps that use n features. So such a linear model is using functions of the form hx. H is a vector now, and it's some weight w1 times the first feature plus w2 times the second feature, and so on and so forth. And it turns out that this the effective dimension of this linear space is equal to the number of features. So this is related to the fact that whenever you take n vectors that are linearly independent, if you stack them into a matrix and these vectors are of length n, then the matrix will be full rank with probability 1. So this is a result from linear algebra, essentially. And I have explained this in more detail in the book. No, so there's one question. Should it be? No, it's already when you have n larger or equal to m. No, you can perfectly fit m data points as soon as the number of features is large enough. So the number of features has to be large. So it must be n larger or equal than m. You can go over the proof in the course book, chapter 6. Or tell me, point me out a mistake in my derivation, but I have double checked it. I hope. So this tells that the effective dimension of linear predictors is equal to the number of features that you use in a linear predictor. And remember, the number of features, for example, for an image is the number of pixels. And modern cameras have megapixels, take megapixel images. So it's millions. The effective dimension of linear maps here is then millions. Another example, polynomial regression. So the set of polynomials of degree r, the effective dimension here is r plus 1. You can perfectly fit any m data points using a polynomial of maximum degree r as soon as r plus 1 is larger than or equal than the number of data points. So this also is related to the fundamental theorem of algebra. Okay, so to illustrate this point, look at 2 data points and r equal to 1. So polynomials with maximum degree 1. And then any 2 data points that I give you, you can fit with a straight line. A polynomial is a straight line. So I tell you this blue pair of points, you find the blue curve perfectly fitting these 2. I give you this yellow 2 points. You find another curve perfectly going through these 2 points. Let's put this one higher. So I give you 3 data points. You will find a degree 2 polynomial, which is a quadratic function that perfectly goes through 3 data points. So the effective dimension here of this space is 3, because you can perfectly fit any data set up to 3 data points. Yeah, and the point is that the effective dimension of the models used in modern machine learning is very large. So as I said, the effective dimension of linear maps is the number of features, and it's not uncommon to use millions of raw features. So the dimension is here millions. The effective dimension of the of a deep network, of an artificial neural network, is more or less on the order of the number of tunable parameters, and there are deep networks which use billions of tunable parameters. So effective dimension of these models is billions. And by definition, as soon as the training set is smaller than the effective dimension, we will most likely overfit. So this large effective dimension requires us to use huge data sets with a number of data points on the same order. Okay. So the general behavior is like this. If you use a model and compute the training error by minimizing the training, so you minimize the training error and then validate it. When you increase the model, when you make the model larger, like you use polynomials with larger and larger degree, the training error goes down because you have larger and larger models which contain more and more new hypothesis maps that can even better fit the training data than the smaller one. However, you run more and more into overfitting, and at some point the training error will be 0. This is exactly when the effective dimension is equal to the number of data points. So this is a threshold, this is a critical value. And beyond that, the training error is 0, looks very good on the training set, but the validation error increases. You will more and more kind of take up noise in the training, and with the result of increasing the validation error. Yes. So this is the basic behavior of the training and validation error as the effective dimension of the model increases. Yeah, this is related to a bias variance trade-off. Indeed. So now we are at the end of today's lecture, which was quite extensive. So the take-home messages of this lecture are modern machine learning methods use very large models, like linear regression models with a lot of features give very large hypothesis spaces. And artificial neural networks with billions of tunable weights are also very large models. So, and they tend to overfit unless you have really large amounts of training data. And we rarely have this. So we need to probe and validate the learned hypothesis outside the training set. So this is mandatory. As soon after you train a model, you must validate the hypothesis that you get from the learning process. You must validate this hypothesis outside the training set on a validation set. Then if you have several models or candidate models, you choose the model based on the smallest validation error. And as soon as you use the validation error to choose a model, you must then test the finally chosen model on a test set. So you have a training set, a validation set, and a test set. So what's next? Today, we mostly assumed that somebody gave us a list of candidate models, like I. So Alex gave you an idea for a list of candidate models like logistic regression and decision trees. But then in practice, how do you come up with a good list of candidate models? They don't fall from heaven normally. Nobody tells you that. This is something you as a machine learning engineer have to develop as a skill to guess a good, what could be good candidate models. And to this end, we will see in the next lecture that there are certain ways to diagnose machine learning methods, and this diagnosis reveals potential candidate models, different models that should be that should be tried out. And then after this, the last lecture of this round will be on regularization, which is a very elegant way to tune this size of a model. So to make a hypothesis space smaller or larger in order to navigate this training validation error curve. So we want to find the sweet spot here with the small validation error. And in order to find, to get to this place, we must change the ratio of effective dimension to, or we must change the effective dimension. And the regularization techniques are very efficient method or technique to change this effective dimension, just to blow up or shrink the hypothesis space appropriately. Okay, thank you. Any questions at the end? Yes, so if you have data which is already split it into training and test, then you take the training part and split it further into train and validation. Yes. Yeah, the slides are, I will put the slides in the material, and you can find already the slides on the lecture section. For this lecture, I have added the slides there. Yes, you can also split twice with this train test split. So you take, you read in all the data you have available, pool them together in one big table, and then you do the first split into a train validation set and a test set, and then you split another time this train validation set into training set and a validation set. If you use a pre-trained model, well, you can still use it, you can still fine-tune it and get a training error on this fine-tuning. Yes, so if you need help with programming questions, please reach out directly to TAs by email, or even better, in the exercise sessions. I think the score, the logistic regression score is 1 minus error, but I'm not sure. So please look up the documentation of scikit-learn. Then another question. So if my machine learning problem is to do with weather data, should I just ignore the fact that the previous days affect the following days? Yes. Treat them as independent as a first approximation. Yeah, if you only use one model in your report, then you should really have a good argument for using only one model and not doing a sanity check with a more simpler basic model. But if you, I highly recommend to use a second model and then do validation, compute the validation errors, and then the final test error. Okay, so There's another question. In the report, you split the data training and tested by random from the total data set. For example, in the example report, the training set was from winter and the test from, in other words, the split were not made by random. Yes, yes, that's maybe not optimal. Yes, maybe not optimal, but such details are beyond the scope of this course. Don't worry about this potential correlations in a time series. We don't know what time series are in this course. Don't worry about that. But you're right. In practice, I would not do this split from different years. Might not be such a good idea, but for the project, it's okay. If you got an error or if you had a mistake in the quiz, I will only discuss this next week after the quiz is closed. Was it that, then another question, was it that the usefulness of the random variable assumption in ERM is that we can get solutions to the optimization problems related to enclosed form? No, so this assumption of data points being realizations of IID variables is kind of used to motivate empirical risk minimization, because why should we minimize the average loss on a training error? Why should we compute the average loss over different data points? So it's not clear why this should be optimal. However, if the data can be at least approximately considered as realizations of IID variables, then empirical risk minimization makes sense as an approximation of the average risk. So the question is, if the project report is so short, how do we present our computation code? You don't need to include code, so no need to include source code. Please look up the reviewer questions on the My Courses page. They should give you an idea what you should put into the report. And definitely, we do not require to discuss code there or even copy paste source code there. This is not required. So quiz 4 has 5 short questions, and it once you start an attempt, so you have a single attempt and you have 2 hours. Within those 2 hours, you have to submit your solutions. That's a very good point. So a very good question. Can I use the previous 7 days values as separate 7 features to predict the next day's value? Perfectly, yes, yes. This is done by, this is called auto-regressive models, by the way. Any other question? You can always contact us or me directly by email. Do not hesitate to ask by email. Okay, so I will now, one last question. Can we consult you about the ML project? How can we? Yeah, the preferred option is that you join the exercise sessions that I will attend. So I will now pick 1 or 2 exercise sessions also next week where I will be present. And there you can bring up and present your project and your questions. But you can also ask them by email to me. Okay, so we'll now end here. Thanks a lot and have a nice evening.